Imagine floating in a vast empty ocean where the closest sign of life is billions of light years away. It might sound like science fiction, but it could actually be our reality. For years, astronomers have debated whether our Milky Way galaxy is located near the center of an enormous cosmic void, but for decades they were uncertain. Now, new images from the James Webb Space Telescope, JWST, suggest that we might indeed be inside a gigantic cosmic void. This discovery could help solve one of the biggest mysteries in cosmology. Get ready for a surprise because what the JWST has uncovered might change everything we know about the universe. To understand this discovery, let's first take a look at how the universe is structured. The universe is like a vast cosmic web consisting of filaments of matter, mostly dark matter, interwoven to form a large-scale network. Galaxies and galaxy clusters, which are massive groups of galaxies bound together by gravity, sit at the intersections of these filaments. But not all of space is filled with matter. In fact, vast regions of space, known as cosmic voids, contain very little matter at all. These voids are like giant bubbles or deserts in space, where stars, planets, and galaxies are sparse. Cosmic voids can be extremely large, stretching millions of light years across. To put that into perspective, traveling at the speed of light, roughly 300,000 kilometers per second, it would still take you millions of years to cross just one void. Some recent studies even suggest that supervoids, which are even larger, could span billions of light years. Now here's where things get strange. According to our current cosmological models, these massive voids shouldn't exist at all. If they do, something fundamental may be wrong with our understanding of the universe. A key idea in cosmology is the cosmological principle, which asserts that the universe is homogeneous and isotropic on a large scale. But what does this mean? Let's break it down. When cosmologists say the universe is homogeneous, they mean that on the largest scales, the universe looks the same everywhere. Think of it like looking out over an ocean. Up close, you might see waves, fish, or boats. But if you zoom out far enough, the ocean looks like a flat, featureless blue surface. In the same way, if we zoom out on the universe, everything, galaxies, stars, and planets, appears to spread out evenly without large clumps or empty regions. So, homogeneous means the universe has a consistent composition when viewed on the grandest scales. Isotropy refers to the universe looking the same in every direction. Imagine standing in the middle of a desert. No matter which direction you turn, the view is the same. In terms of the universe, isotropy means that from any point in space, if you look out in any direction, you should see a similar pattern of galaxies and cosmic structures. There's no preferred direction. Everything is evenly spread out, no matter where you look. This cosmological principle has long been one of the key assumptions in cosmology. It also implies that the universe is expanding uniformly. Wherever you are, everything around you is moving away at the same rate. But this expansion doesn't mean the universe is expanding into something else, or that there is a central point from which it's expanding. Instead, space itself is stretching, and this happens uniformly across the entire universe. However, recent discoveries from the James Webb Space Telescope challenge this idea. The telescope has found that the universe might not be as homogeneous and isotropic as we once thought. In simpler terms, the universe may not be the same everywhere or look the same in all directions. The JWST has observed distant galaxies that appear much older and more developed than expected based on current models. These galaxies are organized in ways that suggest significant differences between different regions of the universe. If these observations are confirmed, it could mean that large-scale structures like galaxy clusters are unevenly distributed across space. The discovery of a massive ring-like structure of galaxies also challenges the idea that the universe is isotropic and homogeneous. If the universe were uniform in all directions, such a distinct, large formation shouldn't exist. This suggests that matter isn't evenly distributed, and cosmic structures can vary greatly over time and space. This brings us to the possibility that vast cosmic voids could exist within the universe. Recent research suggests that our Milky Way galaxy might be located at the center of a supervoid, an enormous empty region in space about 2 billion light-years across. The presence of this supervoid could help solve one of cosmology's biggest mysteries, the Hubble tension. The Hubble tension refers to a perplexing problem in measuring the universe's expansion. When astronomers use different methods to measure how fast the universe is expanding, they get different results. One method measures the expansion rate of the nearby universe, while another observes the distant universe. The problem is that the two methods yield conflicting results, with the nearby universe appearing to expand faster than the distant universe. This discrepancy is what we call the Hubble tension. A new study led by scientists Serge Mazurenko, Indra Nilbanik, Pavel Krupa, and Moritz Hasselbauer tackles this problem. They examined a massive region of space known as the Keenan, Barger, and Cowie (KBC) supervoid, which is about 300 million parsecs in diameter. This region contains far fewer galaxies than expected and poses a challenge for the standard cosmological model, known as the lambda cold dark matter, lambda CDM model. The researchers focused on two key issues: the Hubble tension and bulk flow. Bulk flow refers to the motion of galaxies through space. According to the standard model, galaxies should move at certain speeds. However, new observations show that galaxies near the KBC supervoid are moving much faster than expected. These faster movements don't fit with the current model, suggesting that something unusual is happening. To explain these discrepancies, the researchers applied a new mathematical model developed by Moritz Hasselbauer. This model predicts how galaxies should move in the universe and offers a solution to the mismatch between observed galaxy speeds and what we expect based on the lambda CDM model. Their findings suggest that if we consider the existence of large-scale structures like the KBC supervoid, we can better explain the observed data. Even more intriguingly, the study proposes that our Milky Way galaxy might reside at the center of a supervoid. According to the researchers, if we're inside this supervoid, we would see galaxies and other cosmic structures being pulled away from us toward denser regions of space. As a result, we would observe our surroundings expanding faster than the rest of the universe. This could help explain the Hubble tension, why the nearby universe seems to be expanding at a faster rate than the distant universe. This study offers two important conclusions. First, it provides a new explanation for the Hubble tension, suggesting that the mismatch in expansion rate measurements could be due to the presence of large cosmic structures, like the KBC supervoid. Second, it raises the possibility that our galaxy may be located at the center of a supervoid, offering a fresh perspective on our place in the universe. These discoveries challenge long-held assumptions about the structure and evolution of the universe and could lead to new theories about how the cosmos works. If we truly are inside a cosmic void, it could reshape our understanding of the universe on a fundamental level. Well, that's all for today. I hope you found this discovery as fascinating as I did. Before you go, don't forget to share your thoughts about this groundbreaking research in the comments below. Thanks for watching, and stay tuned for more exciting cosmic discoveries.